Okay, in this video we're talking more about confidence intervals for the mean. And this time we're not going to assume that we know the SD. You might have been wondering about that in the last video, like how do we know all of these SDs? And that's a valid point. In most real-world applications we won't know the SD and you have to deal with that. In the last video, all of the questions assumed that we happen to know the distribution variance and SD, and this led us to use the Z distribution. But if you don't know this parameter, then you end up with a new type of distribution called the T distribution. So here are a couple of really quick facts about the T distribution. First, there's not just one, there's many of them. It depends on something called degrees of freedom, and that's a concept you'll see again in the future too. Lots of distributions have degrees of freedom and they affect the shape of the distribution. All T distributions are bell-shaped, symmetric, and centered at 0. They look a lot like Z, except they have a slightly larger variance, so they are a little bit fatter. And for comparison, here is the Z distribution compared to one example of a T distribution. You can see how the T distribution has the same mean, but a larger variance. Okay, to get the T distribution, we begin with our Z formula. In the last video, we assumed that we knew the population SD. But we're not going to assume that in this video, and this is a far more realistic situation. All we have to do is replace the population SD sigma with the sample SD S. Making that substitution changes the distribution from Z to T. And specifically, we get a T distribution with n-1 degrees of freedom. The degrees of freedom in a T distribution affect its variance. Generally, fewer degrees of freedom mean a larger variance in the distribution. The more degrees of freedom mean a smaller variance, although there is a limit. As the degrees of freedom get larger and larger, then the T distribution converges toward the Z distribution. And a T distribution with infinite degrees of freedom would exactly equal the Z distribution. And here's a picture of what's going on. The black line represents the Z distribution, or a T distribution with infinite degrees of freedom. And you can see that as the degrees of freedom get less and less, then each T distribution has a larger variance and is wider. And these numbers along the x-axis represent their respective percentiles where the tail area is 2.5% area. You should recognize the Z distribution percentile 1.6 from the previous videos. And then you should notice that as the degrees of freedom get fewer and variance gets larger, then these percentiles are farther and farther from the mean. In the back of your book, there is a T-table that looks kind of like this. Along the top row, you have various tail areas. You can see that in the picture here. And going down the left side, you have degrees of freedom. Each row is a different T distribution with its own unique degrees of freedom. So this is pretty different from the Z table. Since there is only one and only one Z distribution, the Z table is very detailed and you can find almost any area that you desire. But there are many possible T distributions because it depends on the degrees of freedom. In order to make a T table with the same level of detail as the Z table, you would need hundreds of pages, one for each different degrees of freedom. And that would be just a huge waste of time. We can get a lot of work done just by knowing a handful of numbers, the percentiles that give us the important tail areas like 10%, 5%, and 1%. So the T-table doesn't try to be complete, it just distills each T distribution down to a handful of important percentiles, and that's the only information it gives us. So let's use this to do a question. We're going to make a confidence interval for the mean, and this is what we know: the sample size, the sample mean, and the sample SD. In real life, after we collect data, these are typically the very first things that we would calculate from it. We're going to make a 95% interval, so we begin, as always, with a statement about probability. Since this problem does not assume that we know the population SD, we know that we are going to have a t-distribution, and since the sample size is 13, we know it has 12 degrees of freedom. In order to find the middle 95% of the t-distribution with 12 degrees of freedom, we need to look up 12 degrees of freedom in the t-table and search for the percentile that has 2.5% tail area. The table tells us this number is 2.179. So this is the probability that t is between plus and minus 2.179 is equal to 95%. Next, we're going to replace t with its formula, just like in the previous video. And then we're going to plug in all the values that we know: x bar, s, and n. We plug them in and we solve for mu, and eventually we arrive here. So mu is between 63.86 and 70.14, and there it is in interval notation. And this is the 95% confidence interval for the unknown mean of all students. Notice again that the pattern is just like the last video, so that the center of the interval is x bar, and from there we extend a certain distance left and right. The only differences are that the population SD sigma is replaced by the sample SD S, which means that this is a t-distribution percentile instead of a z-distribution percentile. Otherwise, it is exactly the same. Okay, in this question, we are given the confidence interval, and we need to figure out the confidence level. So first things first, there are 23 degrees of freedom since the sample size was given as 24. We need to find the center of the interval because that would be equal to the sample mean, or x bar. And that turns out to be 23.15. The confidence interval can then be written as x bar plus or minus the half width. And the half width is equal to t times s over root n. Plugging in s and n and solving for t, we get t equals 1.714. Remember that we have 23 degrees of freedom, so looking along that row in the t-table, we see that this corresponds to a tail area of 0.05. Since this area must appear in both the left and right tails, this means that we have the middle 90% area in the t-distribution, therefore we have 90% confidence. In this last example, we're going to do a new application of confidence intervals. We're going to extend a confidence interval to a larger population by multiplying the endpoints of the interval. Let's begin by making the 95% confidence interval as usual. We have a sample size of 20 and therefore 19 degrees of freedom. If we look this up in the t-table, then we see that the middle 95% of the distribution is between plus and minus 2.093. Plug in the sample mean and the sample SD, and the interval is 623 plus or minus 166.6, or between these two numbers. And this is for the mean amount spent per person. The total amount spent by a group of people is equal to the mean times the number of people. So if we take the confidence interval for the mean and then multiply its endpoints by 1,500, then we'll have the confidence interval for the total amount spent by 1,500 people. Okay, you have 3 questions coming up. Good luck with that, and check out the next video.